Hello everyone, I'm Daniel Diaz Romero, and today I will explain to you how to do the following exercise. A thin non-conducting rod of finite length L, which is the one represented here, carries a total charge Q spread uniformly along it. Show that E at point P on the perpendicular bisector on the figure. Okay, so first of all, I need to explain to you what is an electric field. An electric field goes alongside with a vector field, which has magnitude, direction, and sensory, and has the particularity that it decreases as you move further away from it. And also, the fields in general, in this case the electric, can be described with the Coulomb's law. The Coulomb's law is the following: Q over Q1, Q2, R squared, and Unitarian vector. This is the Coulomb's law. Okay, Q is the constant, which is 1 by 4p epsilon 0. Qt is the magnitude of the charges. R squared is the distance squared. And R to the hat is the Unitarian vector, which expresses the magnitude uh, who has a norm per component and can be described like this. It's here. All right. And also, this goes alongside with the fields in general. A field can be described as an exerted force at a distance over a punctual charge. So, in order to calculate the field, which is what we want to do, is equal to the main force over an exerted force, an exerted point, sorry. But, and here is where is the Coulomb's law takes action. If you don't know what the F vector is of the force, you can overwrite the equation, bending it with the Coulomb's law, which is the constant of Q1, which is once again the magnitude of the charge, over R squared, which is still the distance, multiplied by the Unitarian vector. All right. So now that we have all this information, let's analyze further the problem. So mainly, as you can see, we have two triangles that can be described as two vectors, the sum of two vectors. And this has the particularity to express Pythagorean trigonometric Pythagorean trigonometry. Pythagorean trigonometry. So if we want to know the electric field, then we need to get these values. But only we do know that if we manipulate our data, here's y and L, we can define that L could be described as our main distance. So firstly, because this is a transparent triangle, we are going to consider this as the main problem. Okay, so we have theta here, and this will be the hypotenuse. The opposite on the adjacent. The hypotenuse will be the L squared plus y squared. So because we want the distance, we can assign it to the sine function. Sine function of of theta. Why do we have to assign this function? Because, as you may know, we are taking the Unitarian vector, which is this one over here, which can be represented like this. Because we have, and here is a little bit of theory, these two vectors can be also represented like this. As you may see, the x vector, the x vectors and the y vectors they are practically the same, but the x vector cancels out because they collide with each other. So we only have to consider out the y vectors. Those sum up. So you have to have this in mind in order to achieve the result. So without the information we know, is the R, the unitary vector, can be described also as the axis over the hypotenuse square with the norm, sorry, which would be the same as x is equal to E, which is the field cosine of theta, and y sine of theta, which is where we get this conclusion, sine of theta, which will be the main distance. But here, we don't want the axis because of the same reason I told you about a few minutes ago. Because the x-axis cancels out. So we can rewrite the function as if it were E, it's equal to K to the Q function, the Q over R squared, and R is the unitary vector, now can be represented as 2 sine of theta. The number 2 is once again, this axis cancel out, and we have 2 y-axis, which sum up. So that's the reason we put the 2 over here. But there's a main problem. We don't want to work out with the angle values because they are going to overcomplicate everything. So in order to translate that value and replace it with something we may know, we do know that the sine can also be described as the opposite leg over the hypotenuse. Here we have the opposite leg and the hypotenuse, which can be transcribed as y over L squared plus y squared. So this is equal to R, the main distance. All right. So now we have our substitutions. Oh, sorry, this isn't equal to R. It's equals to the 2 sine. I got confused, sorry. So because here's a 2, would be equal to Q R squared over Q is a constant, so we can put it right here. And here we have dq, which is the derivative of R. In a moment, I will bring you how we get that conclusion, which is kind of the same over here, which is L squared plus y squared, 31.5. And this is going to be multiplied, I will read this for a moment, to y, which is the main function over here, alias the Unitarian vector of L squared plus y squared to 1.5. All right. As I mentioned earlier, R is also a sine function, so it shares the same DNA of the sine correction. That's why I got confused. So anyway, we have to move on. So we do have the function over here. So now we can multiply each term, and that would lead us to the function over here, the equation over here, 2k y dk, these ones, over L squared L squared plus y squared to 3.5 because of the terms that are right here. So now we have this main function and we can't reduce it anymore. One important thing, and here we're going to talk about theory a little bit more. We have dq over here, but we know because of linear density, which is mass over the linear, This is linear density. But the linear charge density, instead, charge density, which is expressed by the lambda symbol, is the charge over the length, that is length right here, and the charge over there. So it's equal to Q over L. So with that conclusion, we know that Q is equal to lambda multiplied by L. Therefore, the derivative of Q and the derivative of L can be also be transcribed as lambda, which also means that dq is equal to lambda multiplying the derivative of L, which is the same as Q, or dq in this case. So we can transcribe this function as y yeah, that's right. Lambda is a constant, so we have to put it right here. And the L is not, so goes alongside of the interfunction. S squared plus y squared to 3.5. And now that we reduce our function as much as possible, we have to integrate this function. So now let me erase all of this to get moving forward. Oh, something I forgot to mention about lambda is that it only works once the Q is uniform, as we can see here, because they share the same charge in all the surface. That's a property of lambda. So we have this, and we can't rearrange this function any further. So now we have to get the integral of this function, which would be the integral of 2 lambda, dy lambda, sorry, I forgot to put it, dqy lambda over dl over L squared plus y squared to 3.5. So, in order to integrate that function, we need to use or to resolve it by utilizing the integral by trigonometric substitution. All right? So, as the name says, we have to use, once again, Pythagorean properties. So, in order to make this thing easier, we don't want DL because that overcomplicates our things. Once again, the main is the reason that we want to do this type of integrals by trigonometric substitution is to substitute some values with trigonometric properties. So to make our things easier, we will arrange as L if it were on the y-axis and y on the x-axis to simplify things. For the arrow, I'll get that in a minute. And now we have here the hypotenuse, which is Ly L squared plus y squared. That doesn't change. So we want to substitute L, which is here. And to get that object is the opposite leg over the adjacent leg. And which function does it work with both legs? The tangent function. So the tangent of theta is equal to L over y. But we do some substitution. So L is equal to y tangent of theta. But that only gives us our L value. We want the derivative of L. So we derive the function, which by trigonometric properties is equals to y secant square of theta d theta. All right. So once we have these arrangements, we can start substituting the lines. So we have integral. Since all of these are constants, we can arrange it on the other side to k, sorry, or well, the constant j lambda, and now the integral. Further, we're going to do the evaluation from 0, or when from a to b. Just to keep it in mind, it's the defined function, but we are not going to concentrate in that for the moment. And now we substitute dl, which is y secant square of theta d theta over s squared plus y squared 3.5, which can arguably be the same as it was earlier. 3.5. Okay, so now what do we do? As you may notice, we can substitute this term right here, because as you may see, there's an L and a Y component as well. So, as you may have seen, we already have took this component, but you have to remember that it's squared. So, would be the same as y squared tangent squared of theta plus y squared. And all of that to the 3.5. So, as you may have noticed, here are some similar terms. So we can factorize in order to reduce our function, which could be y squared equal 3 to the half, y squared, sorry, the 3 to the half. And now the substitution, which is tangent squared plus 1. That is tangent of theta plus 1. And this right here is a Pythagorean function. So we know that tan square plus 1, it's equal to secant square. So we're going to take advantage of that in the future. Also, as you may have noticed, here we can reduce terms. So the development of this y function would be y squared over y squared from 3 to the 2. That would be the same as y to the 2 over y to the 3, alias y to the minus 1, which would be the same as 1 over y. And this may also be a constant as well. So we can get it out of the main function and put it right over the constants. So it will be the same as 2k y lambda, sorry, 2k lambda over y. And secant square theta d theta over, and as you might have noticed, here is also a tangent square, so we can replace it with secant square of theta because of the trigonometric identity that I showed you a little bit earlier. No, it's only secant theta 3.5. So now we can reduce these terms, and similar to 1, this will be the same as 2 minus 3 is equal to secant minus 1 alias 1 over secant. And this can be transcribed because this is another trigonometric identity. 1 over secant is equal to cosine, as well as the secant is equal to 1 over cosine. So, as you may know that would be the same as having 2k lambda over y, now with the derivative of cosine, which remember this was 1 over secant cosine of theta. And because d theta, because we have the cosine, and now we, as you remember, now we have to integrate this cosine. So the integral of cosine, as you may know, it's equal to sine. So we can now integrate this as it is mainly supposed to be to 2k lambda over y of sine, which is the integral of the main function of theta from a to b. And once again, we have another sine function, and we don't want to work with that. So we can replace it as we did already. The sine is equal to the opposite leg over the hypotenuse, which can be transcribed as L over L squared plus y squared to 1.5. So we replace this with this new function, which would be 2k lambda over y of L of L squared plus y squared to 1.5. From A to B. All right. So now let me erase all this mess so we can get to next point, which would be the evaluation of the main points and the integral. But we can also rearrange the integral once again. All right, let me translate this main function over here. E is equal to 2k x lambda, sorry, over y of L squared plus y squared to the 1.5. All right, evaluated from A to B. So now, as you may remember, lambda is equal to Q over L because of the function polarity. So what this means is that we can replenish lambda once again with E it's equal to K of lambda over Y, but lambda now is Q over L, which can cancel out with this one over here. So we can rearrange the function as the following. Q, and here's a 1, of L squared plus Y squared 1.5. All right. So now we can begin with the evaluation. As I mentioned earlier, the evaluation, because of the function polarity, should be a half of L, as you may have noticed, which would be this area over here, right? So now we have to rearrange the function once more in order to evaluate correctly. So we do know that our evaluation, we are going to do it right here. It's L is equal to L prime. We are doing this so need to, in order that we don't get confused, you know how variables work. So then it's L to the square root. No, L to the square, sorry. L square, which we already is equal to L prime square over 4, right? Because remember, we're evaluating in L to the 1/2. So we can rewrite this function as L prime square over 4 plus y squared, which would be the other evaluation. That is right here. So now we can play it alongside the forms, so we can get a simpler expression. For example, by multiplying by 4 over 4, because here's another 4. So L squared over 4, and here we need to put y squared. These ones cancel out, so that results on 1/4 of L prime squared plus 4 y squared. And this can be rewritten once again as 1/2 of the function of L prime squared plus 4y squared. Now, we have achieved this, we need to substitute it. So instead of writing this over here, we have reduced our expression. So E is equals to 2kq over y of 1 over L squared over 4. Plus y squared, which is the function that we have been arranging here. So to sum up, we can get to the conclusion that is the same as having, oh, here I forgot the 1/2, very important. All right, it's equal to 2kq over y of the function that we get over there, which is the final one, 1/2 of L prime squared plus 4y squared. Well, instead of putting here, we'll put the 1/2. So, because of this multiplication, that would be the same. I'm going to erase a little bit here. Where did I put the eraser? It's right there, right? That would be the same as having 2 over here. So these two functions sum up, and that is equal to 4k over y multiplying 2 over L prime squared plus 4y squared. And now this will be Oh, sorry, here's a 1, not a 2, because these two multiply. Our final answer. And finally, we can substitute if we still you want. I personally don't because I think it overcomplicates the expression. Decay by 1 over 4p epsilon 0. And that is how we get to the result. Thank you very much and have a nice night.